Think about the chaos of modern software development. Every day, thousands of updates are pushed to public registries. Most of these are harmless, but some are unstable, broken, or worse, compromised. When you pull a package, you are trusting that the version you receive is safe to run. Traditionally, we rely on version numbers to make that decision. We say we want version 1.5, and we get it. But version numbers tell you nothing about when that package was created. A version released 5 minutes ago looks identical to a version released 5 years ago in terms of the number itself. This creates a blind spot. If a malicious actor pushes a bad update, or if a developer accidentally breaks a build, your system can ingest that instability immediately. There is no built-in cooling-off period to let the dust settle. Here is the thing. The current research landscape focuses heavily on resolving conflicts between dependencies. Papers like the one on hypergraph dependency resolution discuss how to unify heterogeneous package managers. Other studies on Python supply chains highlight the prevalence of vulnerabilities. Yet none of these formal models propose a way to enforce a time-based restriction using expression languages. This is where a specific capability of the common expression language comes into play. By utilizing the now function, we can introduce a strict publishing freeze. This effectively blocks the installation of any artifact published within a defined window of hours. It is a preventative security measure that shifts the focus from static version constraints to dynamic, time-aware policies. Consider the specific context of machine learning artifacts. In this domain, models and datasets are treated as packages just like libraries or binaries. When a team trains a new neural network, they might push it to a registry for testing. If that model has a subtle regression, you do not want it deployed to production immediately. If you enforce a cooldown period using the common expression language, the policy engine checks the publication timestamp against the current time. If the difference is less than the threshold, the installation is denied. This prevents the propagation of unstable releases before the community has had a chance to vet them. Now consider this. Implementing cooldowns via this method introduces a trade-off. You are trading immediate access for stability. If a critical security vulnerability is discovered, a patch might be released urgently. A strict age check could inadvertently block that legitimate, urgent update. This is a significant risk. The logic must be nuanced enough to distinguish between malicious rapid releases and normal development cycles. You cannot simply block everything for 24 hours without a mechanism to override it. This requires pairing the cooldown with robust anomaly detection. If the system identifies a known security signature, it should bypass the time restriction. Without this exception handling, you risk creating false negatives for fast-moving, legitimate security patches. The shift towards using expression languages like the Common Expression Language for dependency resolution marks a transition in how we think about software supply chains. Previously, policies were static. You defined rules about which versions were allowed, and those rules did not change based on the clock. Now, we can enforce real-time publication restrictions at the registry or client level without requiring changes to package metadata. The metadata remains the same, but the policy engine adds a layer of temporal logic. This means you do not need to ask package maintainers to change their upload processes. You simply configure the enforcement layer to apply the rules. Let us look at how this works in practice without getting bogged down in technical syntax. Imagine a policy rule that says the current time minus the publication time must be greater than a certain value. If the publication time is too recent, the expression evaluates to false, and the operation is blocked. This is a precise, policy-driven temporal constraint. It allows package managers to programmatically block installations of artifacts published within a defined window. It mitigates zero-day supply chain risks by giving you a buffer zone. It acts like a quarantine period for digital goods. However, this approach is not a standalone solution. It is a layer of defense within a broader security strategy. The research suggests that while cooldowns are a powerful defense against compromised registries, they are not a silver bullet. If an attacker waits for the cooldown to expire before pushing their payload, the protection is bypassed. Therefore, the implementation must be part of a larger ecosystem that monitors for anomalies. You need to know what normal behavior looks like so that you can spot when a new release deviates from that pattern. The time-based check is the first line of defense, but it must be supported by behavioral analysis. There is also the question of architectural requirements. To make this work effectively, the system needs access to accurate timestamps. If the clock on the server is manipulated or if the registry does not store precise publication data, the policy fails. This requires a trusted source of time and a registry that supports granular metadata. It also requires the policy engine to be fast. If every package installation triggers a complex time calculation, it could slow down the development workflow. The Common Expression Language is designed to be performant, which makes it suitable for this use case. It allows for the evaluation of these temporal constraints without introducing significant latency. The implications for machine learning operations are particularly profound. In ML, models are often large and slow to rebuild. If a bad model is deployed, the cost of reverting it is high. A cooldown period ensures that the team has time to review the new artifact before it affects production systems. It forces a pause that encourages human review. It slows down the velocity of deployment just enough to catch errors that automated testing might miss. This aligns with the goal of improving interoperability and visibility across languages mentioned in the broader dependency management literature. Ultimately, this represents a distinct gap between current formal dependency models and real-time publication restrictions. We have established robust semantic foundations for understanding what dependencies are problematic. We know how to resolve conflicts, but we have not fully explored how to prevent the introduction of problematic dependencies in the first place based on time. By utilizing the now function, we can close that gap. We move from a reactive stance, fixing problems after they occur, to a proactive stance, preventing them from reaching the production environment in the first place. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.